Okay, guys, thanks for staying here. In this session, the example will be more realistic, and I'm going to introduce some physics first, like what are the proton PDFs, nuclear PDFs, and fragmentation functions. And in the tutorial this time, we're going to fit the gluon PDF with a neural network, right? Let's start. This is a layman's introduction, so I'm trying to simplify here the concepts, just in case you're not familiar with PDFs. So when we look at a proton, at a free proton, as you know, it contains quarks and gluons. And the way, like the amount of quarks and gluons in the proton, or their distribution in terms of momentum, is captured by functions called PDFs. So let's say the probability of finding a quark that shares or that carries momentum fraction x of the hadron's momentum. So let's say U carrying x fraction of the momentum of the whole proton. This probability is what PDFs are. So as simple as that. And similarly, you can define it in the nuclei. So if you take a proton out of a nuclei and you look inside of the proton, bound with other neutrons and protons, you can define the similar quantity, PDFs. Now, the problem is, or the interesting physics is, that these guys turns out to be different. So the moment you look at protons inside of a nuclei, they give you different dynamics or different probability to find quarks and gluons sharing some X from the nuclei. And this plot shares, I mean, if you plot the ratio between the PDFs of the nuclei versus PDF of the proton, you can see this quite clear difference from one. They're not the same. And these have been studied for the past 60 years. There's a different dynamics called shadowing, anti-shadowing, and EMC. So this was the first actually effect that was discovered of the difference, and it's quite a big impact or effect that is not yet fully understood until today, if you want. And then you have a different function called fragmentation functions, which encodes the probability of producing a hadron from a certain quark. So say you bump an electron into a proton, you get a quark breaking out. This quark, due to QCD, cannot stay as a free quark due to the asymptotic freedom. So it has to fragment into other directly into gluons, and the gluons would fragment into quarks until it reaches a balance, which is a hadron. And the fragmentation function basically dictates or translates this probability. So these are like three different functions that QCD, quantum chromodynamics, doesn't predict them. So you need to extract them from the data. So how do we extract them from the data? Due to factorization theorems, basically, where you introduce renormalization to basically be able to separate a part of the cross-section or the scattering probability into a part that you can calculate, which I call perturbative, and the part that you need to extract from data, a renormalized quantity, which is called PDF, nuclear PDF, and fragmentation function. So this is a bit the context we'll be working with right now. Any questions so far about this? Any, like, I don't expect you to get the full, but you get the gist of the PDFs. And okay, interrupt me if you have a question. So this is basically what I want you to understand. This is the conclusion of the context, but for a more physical definition, one can look at the actual definition of PDF. So if you basically take the hadronic structure, so if you take deep inelastic scattering, okay, you're scattering an electron of a proton, and you have this proton scattering into many quarks and many hadrons itself. So to compute this this tensor, right, this hadronic tensor, you can't do it from first principles. So you can write it that way, basically, the most formal way to write the hadronic tensor, where you sandwich basically the proton state with the quark electromagnetic current and the X state, which you don't know what it is really. And this by use of the factorization theorems and the renormalization group equation, you can formulate it as equal to a PDF convoluted with something that you can compute. So it's the same as before. B sigma in green. Okay, I switched the colors for some reason, but these are the H in blue. And the PDFs are the one that you're trying to determine. So when you get data from CERN or JLab or whatever, this data is given in terms of cross-section, differential in some kinematics. In the case of inelastic scattering, X and Q squared. But you try to extract this quantity, which is quite convoluted. You have an integral here, you have a sum. So it's not direct inference as we saw before with the linear model. It's not like a linear model minus data and that's it. You can figure out the parameters. It's quite convoluted. It's inside an integral. This integral I will refer to as this sign, basically. Okay. So similar way to the way you define nuclear PDFs that basically describe the probability of hitting a quark or a gluon inside of a proton, you can define the nuclear PDF, which is the probability of hitting a quark and gluon inside of a proton that is inside of a nucleus. I won't here dive into much detail just to keep time for the tutorial. But what I want you to understand is that we use an assumption here that we can write the PDF of the nucleus in terms of PDF of the proton and neutrons that constitute the nucleus. And that gives us basically a separation between the proton PDF and neutron PDF, which we can also link by isospin symmetry. But anyway, let's move on. So the last functions I want to look at is fragmentation functions. So the moment you identify a hadron from a collision, like electron positron annihilation or DIS, the moment you measure a hadron, this is where you step into semi-inclusive processes where you need to fit fragmentation function in addition to PDFs, which basically translates the probability of H fragmenting from a certain quark or gluon. So one of the collaborations that fits these functions, PDFs and fragmentation functions, there are many collaborations now. NNPDF is the oldest one. There's also a collaboration called MAP, where they basically decide to parameterize these PDFs and fragmentation functions in terms of neural networks. Why? What's the motivation? Since QCD doesn't give you the functional form of these functions, so you don't know if it's a cosine, a polynomial, a Legendre, it could be any function. And since, if you remember in the previous session, we said that neural network can approximate any function, it seems like a great fit, right, to use neural network parameterization. And that's what these collaborations do. And I've been a former collaborator as well in these, so that's why I will display some results right now. But basically that's it. Sigma, which you can calculate convoluted with neural network. And there are many ways to parameterize these neural networks. So one way, which is the NNPDF way, is to assign an independent neural network per flavor of the quark. So you have up, down, strange, charm, gluon. You define for these 5 or 6 different independent neural networks. Okay. It has this architecture for NNPDF, the version 3.1. okay, we don't care at this point, but the way also, like, you need these neural networks to be PDFs is to also respect some rules from QCD. So although we don't know the form of these PDFs, we know that they have to satisfy certain sum rules. So for example, the sum of all the momentum of the quark gluons should give you the sum or the momentum of the proton, right? This is a simple constraint. So you impose this by adding a certain normalization factor to your neural network, which is f hat I, which is here, right? And you ensure that this always satisfies the sum rule. And there are also other sum rules, like the number sum rule. So you need always to reconstruct the proton quantum numbers, right? So for example, having electric charge of +1, having quantum number, having 2u and 1d, and you can impose these the same way you impose the momentum sum rule. Also, NMPDF uses these prefactors. So we know that PDFs should go to 0 at x equal 1. And this is why they inject this information into the model itself. So they put next to the neural network 1 minus x to the beta, and they also add x to the alpha to control the low x behavior. Finally, the way to extract this convolution of neural networks with these prefactors is by convoluting this Partonic cross-section that we said we can calculate, evolution equations that are also perturbative, with the neural network parameterization. I won't dive in more than that, but you can ask me a question. But this would be the loss function. So it's a chi-squared of the experimental chi-squared. So this theory prediction minus the data over uncertainty, plus a Lagrange multiplier, which I explained in the previous section, where we impose that all the observable that are computed from the neural network, this t, has to be positive, because all physical observable always have to be positive, right? So you impose it as a constraint. And that's it. What you get is, for example, by fitting all this data from CERN, from JLab, from all over the place, you get these probability distributions of the U in the proton, the D bar in the proton, the strange and anti-strange, and the gluon. And you can see that for a certain, for example, energy, you can compute how much momentum strange or U carries in terms of the proton. So these basically are used in all the phenomenology of QCD to predict new observable, or to, for example, if you're making a new experiment and you're trying to see how can you optimize the detectors to find a certain process, you would need PDFs to do predictions and perform your analysis. I will stop here. So I will stick just to proton PDFs at the moment. But what you should know is that there is also another framework for fitting nuclear PDFs, which has completely different architecture, and it has different input features. And you can also see that there's another framework for fragmentation functions, completely also different parameterization, where the positivity of fragmentation function is imposed on the level of the neural networks. This is just to give you some idea of what you can really do with these neural networks. Anyway, what I want you to do is take the gluon extracted from real data from an NPDF and fit it with a neural network. So we're not really extracting the gluon from the data, right? Because you need to convolute. You need to convolute this guy, the gluon PDF, with the perturbative function. But I want just to fit right now the gluon extracted with a neural network. So please, if you can open the notebook, and I will also introduce it a bit before you dive into it. So let me open it here and share the screen. Right. Okay. Can you confirm that you're looking at my notebook?
Yeah, we see it.
Yeah.
Thanks. All right, you can, if you want, skip that. But what you want to know is that I'm taking the gluon, as I showed you before, and I'm considering 4 different files where I have the gluon evaluated from x equal 10 to the minus 3 to 1, 10 to the minus 4, 10 to the minus 5. So I have 4 different data sets, each one with a different range of x. These are loaded into this file, okay? You don't need to change anything. And I'm just parsing this data in this first cell. So this is the first cell, okay? And it would tell me the parsing is done. All right, now I have the data. In the second cell, I'm going to scale the input of the neural network. So this is something I didn't mention, but sometimes it helps in the training to change the mapping of the input that you have for the neural network. So for example, if I have x, which is logarithmically distributed, the neural network would perhaps prefer to see it on a linear scale. Therefore, I should try to renormalize this input feature, x, it could be anything, to something different and see if it gives me a better training. And this is what's done here. So I'm using this scalar to scale the x input, okay? You can read more if you want more details. And finally, the interesting part is that you'll be building your first neural network today with, not your first probably, but I mean, neural network using TensorFlow, the most used library for neural networks. There are 3 versions of models that are written here. We're going to only use once because they're completely equivalent, but you can find them all here. So you have a 3F model, which uses Keras, just a library from TensorFlow. And you can see that you can write a neural network only with a few lines, like 2, 1 to define, 1 to take the n features, right? So you take the n features here and you give it to this layer dense. You specify the number of hidden neurons, and then you take this hidden function and you define an output from it. So this is one hidden layer neural network in 2 lines. And these are other versions of neural networks, so you can define it from the weights and biases yourself. That's was the old way of defining the neural network. And finally, also you can use also yet another way to write a neural network using different functions, basically. So using this, utilizing the NN layer that you defined here, you can use it inside of a model. That just allows you to write a more customized library. But anyway, I don't want you to worry about these. I just want you to know what they do. So these are the parameterization of your neural networks. And now you can use them for something useful. So here I explain a bit the origin of the chi-squared, why everyone tried to minimize the chi-squared. And it starts from a likelihood, the way that you're trying to maximize the likelihood, you end up minimizing a chi-squared of that form, which you probably already know. So you're minimizing your model versus the data weighted by the uncertainty. So if a data has a large uncertainty, this contribution to the chi-squared will be small, and therefore the model won't sense it as much as when you have a small uncertainty. Finally, I will prepare my data split them into training and testing sets, right? So you can also use, where is it? yeah, I'm just splitting here the training and the subset of data from the gluon into training and testing, which you can also, you will be able to play with in the exercises. And finally, I choose my model. So here, for example, I choose, okay, I have one feature, which is X. I choose to have 5 hidden layers inside of the neural network and just one output, which is the PDF of the gluon. All right. I feed these settings to my TF model, which you saw before. And then I define my loss function, which is a chi-squared. So it's a reduced sum of the square of the labels, which are the data, minus my predictions, which is a neural network, over the uncertainty of the data. Then I choose an optimizer. So here I choose a version of the gradient descent that you coded before, but is quite evolved. It's called Adam. It's one of the most efficient gradient descent algorithms. And yeah, I simply define what is a training step should do, which is taking the derivative of the loss and feed it to the optimizer. And then I define a function that computes the loss. And that's it. Let me make sure that I execute the cell. And here I just define a plotting script. So I gather all the information given by the minimizer, and I try to see what's going on. You can uncomment these things if you want, just to see. I mean, I keep it simple, but you can pick whatever you want to uncomment from this. This is just a function, doesn't do anything. Right here, I train finally the neural network and plot it. So there's a verbosity variable here. If you set it to true, so false would just, let's try false first. So false would give you the loss function value at every 1,000 epoch, right? So you can see that the training, the chi-squared of the training goes down, as well the test chi-squared. So you're not training against this, you're only training against this, and you can see it's quite fast. So the ideal chi-squared is when you reach chi-squared over n of 1, which is clearly the case here. And this would give you this following plot. So from this data in blue, you are able to fit with the neural network this curve. And you get quite close to the central value, even though you're fitting, a noise data. And you're achieving a chi-squared of order 1, which is the optimal chi-squared that you expect from a good fit. And you're ending up with a test of 1.36, which is also not bad. You can definitely optimize it. You can get this one to 1 as well, if you want. So just to let you know about this feature, if you put verbosity to true instead, that would allow you to check the neural network every iteration. So this would keep refreshing, as you see here, and you can see the change in your neural network as you go on. It's already very close because it's reiterating over something that is already good, but that's slightly slower than before. Okay, so that's it really. What's interesting here is that I want you to play with the settings that we chose, like the training epochs, the activation functions. Try different activation functions, see the difference between them. Try to increase the architecture of the neural network just to see how better it does. Learning rates of the optimizer, you can change also the optimizer itself. Do as much questions as, pick whatever you think is interesting for you. You can also play with the data set. So I provide here 4 different data sets. I'm using, I think for now, data set 1, which has, x10 to the minus 3. You can extend it below that. I wouldn't care about now advanced exercises for the time being. So just try to focus on these. have fun and let me know if you have any questions. There's nothing to write, no exercise is missing or so on. Just play with the settings and try to understand what's going on.
Well, thank you very much, Rabah. And well, start to working out the exercises. And if you have any questions, just raise the hand and
Exactly.
we'll direct Rabah.
Yeah, thank you.
You can also type it in. You can also type it in the chat if you have problem with the mic or you are too shy to speak. Just throw it in the chat.
Excellent. Thanks, Juan.
You're welcome. Thanks to you.
Hi, Sarah. So, would you care sharing with us this beautiful plot? Tell us how you were able to produce it.
Sure. Pretty much what I did was did 0 hidden layers.
Oh, very good.
Yeah.
All right.
I was curious. I was reducing them, and then it didn't seem to change anything, so I just went to 0. And that managed to change it.
Yeah. Okay. So even with the one, so are you talking hidden neurons or hidden layers?
Hidden. Oh wait, neurons. Okay.
Right. So even with one, were you able to fit the data?
Let's see.
And remember, you have to refresh the notebook because it might. So I would recommend to restart the notebook.
Okay. It's running. Oh, it seems to be converging. 0 is the magic number of not convergence.
Okay, that's actually, it's not surprising because the function is quite easy to learn, right? It's just a very smooth shape. So I know from experience that like you can fit the cosine with only 3 hidden neurons. So for 1 neuron to fit that, I'd be slightly surprised, but not so much. So I will try it myself as well.
Yeah, I get a bad chi-squared, but at least it converges.
Can you share your plot?
Yeah. Let's see.
All right. So this is with 1 neuron, right?
Yeah.
So what happens if you augment the epoch number? Maybe it still can do better.
Augment. What do you mean? Sorry.
Just increase. So there's a, yeah, you see here. Yeah, exactly. Just put it to, I don't know. Yeah.
I'm not sure how far back. I'm just gonna go back to here.
As you wish. Yeah.
Be working.
Good enough. Yeah, it's struggling, right? I mean, with larger architecture, you would see it converge faster.
Yeah.
But it's interesting if it reaches a plateau at 2. Let's see.
I think it's gonna go down.
Oh, there you go.
Okay. Oh, it has reached plateau. Okay.
Okay. So for example, this architecture won't be enough. Like it doesn't describe the data well.
Gotcha.
Yeah.
So the architecture like changes your functional form that
Yes.
you're kind of okay. Yeah. Okay.
It simplifies it, right? I mean, what you're doing exactly is the elementary neural network that, not exactly, well, you have an extra neuron, but it's a very small amount of weight and biases. So it's it's not flexible enough to fit the data.
Gotcha.
Cool. Yeah, that's the first nice example. Thanks for sharing.
No worries. Thanks for sharing these examples. These are fun.
Sure. I would ask you to also check what happens with 1 neuron once you use the data down to x 10 to the minus 6. Perhaps that's also interesting to look at. All right. Does anyone have any question, any interesting conclusions from the notebook? Please share them.
Does anyone have any questions? Are you guys still there?
What if you tried -1 for the for the hidden layer?
1 minute, I can give it a try. I imagine it wouldn't work.
I hope it doesn't, because otherwise the designers of TensorFlow haven't thought that someone would do it.
Yeah, nope, it got angry at me.
Okay.
Expected a positive integer.
Ah, very good. I'm relieved. Anyone did some extreme examples of architectures, epochs or something? 50 neurons or something, I don't know.
I was messing with the input number of neurons and the output number of neurons, and I didn't get very far. It takes a minute for each run to happen. I guess when imagining this to a fit, what would be the best way to like imagine what each of these numbers, input numbers, mean? I suppose yeah.
To be honest, it's not well defined in that problem, because what you're trying to compare against is the data of one dimension, like just have an x and f of x. So the fact that it works means that it's working, but for the wrong reasons. It's just not crashing, but it won't give you anything physical.
Okay.
Because the loss function is written in a way to just compare one output neuron with one array of data. So
Gotcha. Okay. So it just depends on how you set it up.
exactly, depends on your problem. Yeah.
And so the zero, when I did the zero number of neurons in the hidden layer, was that semi-equivalent to trying to fit to a constant?
I was thinking about that actually. What does that mean? So if you look at
I guess no, because even fitting to a constant, I think it still would have tried to converge on something.
in the case where you put hidden neurons to 0, I think you don't have any parameters. Because if you look at TF model in the maybe third cell, yeah, you're not taking, there's no weights or biases, I would say, if I'm not mistaken.
Will there not be one weight between, I guess, the one input node and the output node?
There should be, yes, there should be one. Yeah.
So, I guess the problem would then be that with 0 hidden layer or hidden neurons, there's no nonlinearity.
True.
Right. So it's just output equals W times input.
You're right. You're completely right, I think. Yeah. It's just weight times X plus B. But I think the fact that you're looking at the parallel lines is not that they're parallel. I think this Y scale of the plot is just.
Yeah. It was running away, so the weight must be larger or larger than 1, I suppose, if it's just running away, increasing.
Exactly, yes. Or the bias is just like huge. So it's an offset.
Okay. Thank you.
Ah, interesting. No, thank you. I will share with you another GitHub repository where you can find plenty of other examples of machine learning applied to physics. One of them I particularly like is a notebook set up with deep neural network to find signals of beyond the standard model physics in a sample of data. So I will share it on Slack if you want to have a look. And yeah, thanks for, are we hitting the time, Juan, or is there?
Yes, well, officially the session would end at the 3:50, I would say. But then afterward, we have an informal discussion.
All right.
So what I would suggest, we can officially close the session in 3 minutes, but if people want to stay around, have questions for you, want to continue playing a bit more with the tutorial, they would be very welcome to, if you are willing to do it, of course.
Yeah, yeah, definitely. I'm here.
So that would be my suggestion.
Very good. Yeah, that works.
Hi, can I have one question actually?
Yeah, sure. Go ahead.
Yeah. So I guess in the tutorial, right? Like we are given a data of gluon PDF versus X, right? But like in a realistic research work, like would you say like the value of G, is it gonna be like something secondary? Like wouldn't you need to do like some other plots before to obtain this data?
You would. Very good question. And let me share back some slides, perhaps. Yeah. Yeah. So you can see here. This is now what you're fitting directly, right? So this is your data at the moment, which is, by the way, not physical. Like you can't fit the gluon PDF from some data. There's no data of gluon, but it was just for the sake of the tutorial. But usually, yes, to plot, you can only plot the cross section, which is basically the amplitude of the hadronic tensor, or the cross section, basically. And this is basically the gluon PDF as integrand convoluted with this complicated guy. This is very evolved to compute. And then you sum, there is a sum and there's an integral that goes from X to 1. So indeed, this is how the cross section would look like. It would be in, yeah, go ahead.
Yeah, so I guess my question was like, can you actually go back to the factorization slide? Like, yeah, so you have the cross section that comes from experiments, right? And you have the blue, I guess the blue factor, which you can calculate, right?
Yes. Mm-hmm.
Then do you like deduce the PDF from that algebraically, or is that the work that is done by neural network?
Exactly. So this is an unknown basically, and it has parameters.
Right.
And every time you have 1 point of cross section here, you have to compute many points in the partonic cross section here and multiply, like it's you can see it as a matrix multiplication in a sort of way, but this would be completely random. So it would give you a nonsensical cross section at first. So yeah, these are the neural networks. This is where it is.
Okay. So is it like say you start with some random values of PDF, right? And say when we get a cross-section data, right? We kind of we use the neural network to update the I guess the guess of the PDF, and we evaluate how well that guess is doing by like plug that into the integral, into the convolution integral, and then you compute the resulting cross section and compare that to the data.
Exactly that. Yes.
I see. So it's a little bit of working backward, no? But yeah.
Yeah, it's not a direct relation. Yeah, as you said, I mean, you have to go through this machinery here, the Diglap equation. So these are also evolution equations and Platonic cross-section until you reach the chi-squared, which the minimizer C. So there's like layers of complication before getting to
right. Right, but like at the end of the day, what you're comparing is the cross-section.
Exactly.
Yeah.
Exactly. That's why one of the complications with PDFs is that some cross-sections do not give you sensitivity to all the PDF flavors. So you can parameterize gluon, strange, up, down, but if you're fitting only DIS, the way DIS is computed, it doesn't allow you to, you need them to be linearly independent to be able to fit them. But DIS only gives you access to 3 flavors, for example, theoretically. So you need to inject that kind of constraint or information to your problem. So you only parameterize 3 flavors instead of 6 when you fit DIS, stuff like that.
So for other flavors, maybe you need like CDs or something like that, or?
Yes, Drell-Yan, jet production. The more processes you have, the better. W and Z production. So they would give you different mixing with the PDF.
Right. Yeah, thank you.
Sure, no, thanks for the question.
Well, if there are no more questions, we can officially close the afternoon session. But as I said, we have now an informal discussion, so we can just stay around and continue playing with the code and ask more questions to Rabah for a bit.